and then here I'm saying there is a lambda set which is set all these to be 0, set y1 up to y lambda square to be less than or equal to 1. That's a lambda set. That has to be attached according to that code. Yeah, so these are of course,
yeah. Just as the third one becomes clear from what you see in terms of flows, there are two also become clear.
No, say that again.
Yeah, just as you mentioned, third one becomes clear when you use the flow or given by the using a reminder.
Yes.
And theorem two similarly becomes clear.
Oh, yeah, so the point I guess here is to make things smooth and all, have to do a lot of work. This attachment is just topological, but if you want to sort of attach a thicker version in a smooth manner, you have to, it's not like you have, like something like this and then you attach this thing. This is not a smooth thing, so you have to do a lot of smoothing so I think in the usual setup you spend a lot of time trying to create smoother version of that attachment, but typical picture would be like this. You have your MC minus epsilon, which is like the cylinder, and then you're attaching a one cell, which in this coordinate looks like mod x less or equal to 1. That amounts to informally this picture of attaching a thing here. Then you have to thicken this to get a surface with boundary, deform that to the bigger thing.
Yeah, you're saying that you have to analyze how the flow looks like near that.
Yes. Yeah, so the point is, this is not just something which you can immediately use. You still have to use the local structure and the flows and everything to say how to use it. It's not like you take something and you do anything. You will not just get the right to do it at all. So you have control, but you have to establish all of that. Yes. Let me do the example of the torus. Hopefully to highlight what's going on. And this is going to be exactly the first thing that we did. Right? So you start with the empty set because you're starting at, let's say, n nodes of minus 100. There's nothing there. Okay? And then you look at this. This is a 0 cell because I'm looking at the lowest point and that is index 0. Yes. No, there's no genus. This is just a general manifold. The general manifold. No, but what do you mean by genus? It's a general manifold, right? So there's no notion of genus. Say this is just think of this as some open subset of iron or some appropriate subride or something. You're thinking of surfaces. Surfaces you can call things. This is just a manifold which is locally out. That's not genus. It's just saying that around this point, using those coordinate systems, if you go beyond P and go below P, you need to differ by topologically by an attachment of a lambda disk. But as I said, this with the lambda disk and this, they are not homomorphic. They cannot be. This is not a manifold. That one is. But they are homotopy. Yeah. Any other? Okay, so we start at the bottom. So this is the bottommost point of the torus. This is the 0 cell. There is cell because it's a point of index 0. And then I start moving up. So I basically thicken this. And remember, thickening is a homotopy equivalence. Thickening means what? It means I simply take more of this. They're homotopy because I can deformation things like this to this or they're equivalent to them. Okay, so this is what I get. So far so good. We sort of went past one critical point of index 0, and that essentially means that you had nothing because this was empty, and then you're attaching a 0 cell. Right? So this is literally what this is saying. You had nothing here because it is empty. You went past one critical point of index 0, you're attaching a 0 cell. But attaching a 0 cell to the empty cell is just the 0 cell, which is this, but I can thicken this to get this. Nothing changes so far. Okay, so now I want to go past. Let's see. So now I want to go past. See, you have to imagine this picture, right now we are here. And so whether I go up here or not, it doesn't matter. I mean, this and this, they are homeomorphic or eukaryotic by first place. So now I am going past this critical point. This is an index point. So when I go past this theorem is going to say that. So everything here, by the way, is compact because our M is compact. So all of these are compact. M is porous. If I go past this, I have to attach a one hand according to how the height function looks like at this point. We wrote it down in one setup. It looks like x squared minus y squared in one setup and y squared minus x squared in the other setup. Here, when you do this, you get this kind of picture. So I'm going to let me the color. This is the one that we have attached. This is your this one. Okay. Sorry. When you go past this critical point, you have to attach a one cell or a one disk, which is just linear. And then you can again thicken this. The thickening is the homotopy equivalent. So thickening means what? Thickening means you can see the original one thing inside. So these two are homotopy equivalent. This again is not homotopy. But this again can be made to look like this is homomorphic to something which you all know. This sort of looks like this thing, right? What was wrong? Okay. So now you want to go past this critical point, which is the index point. Which means this tells you have to attach a one cell. And one cell is again an interval. So you have to specify how to attach, and this time is going to attach this to, because remember we saw that it looks like z equals x squared minus y squared in one of them, and it looks like minus of the other. The silent things were way too different. So here you have to go to theorem 2 again. Yeah, so here when you say this is the same as this is the same as all the way up, I'm essentially using theorem 1 over and over. If you are here, you can increase this all the way up to the time you hit the critical point at index point. Just before that, all of them are diffeomorphic because of theorem 1. Once you're here, you have to attach this. If I draw this, this one. Then I'm going to attach and then I have to thicken this. Thickening again doesn't take much. Thickening means something like this, and again here you have original. Okay, so when you're reading this book, sometimes you see the word lambda handle being used. So lambda handle is nothing but a thicker version of a lambda cell. So a lambda cell is by definition just a lambda disk, and a lambda handle depends on the dimension here. It's just going to be take this and you cross it with the complementary dimension so that it becomes an n-dimensional thing. So everything is an n-dimensional disk, but it sort of has a core lambda disk inside. So that's what a lambda handle is. Sometimes it's called handle attachment. So you think of this as a handle rather than cell. Okay. Anyway, so this is what you get. But now you can sort of imagine this is homomorphic to the picture where and then see when you go up, the first thing, when you go beyond this, the top point and index screws, you have to attach a two cell, which is a closed screw disc, and that's like a cap. So here you have to use, here you can see that you simply attach. And then after this, there's nothing, because it's subsumed. Anyway, this is just an illustration. This is why moving the group, this requires some amount of work. It's not entirely trivial. I think we want to get this to the plus, set up things properly, analyze.